you just get which is perfectly reasonable, and it's smooth and it continuously varies. So this one is a smooth parameterization. So the important thing here is that to realize is that it's not like just a picture that you should look at if like something is a smooth curve or not. It really depends on the parameterization that you need to look at. Some of the parameterizations, if you plot them, they might not look smooth. So that's really something you should keep in mind. That, like, yeah, you should just take the derivative and see if that's like continuous. But like maybe something to note here, which which is like important, is that this point where you have a cusp like this is still special. Namely that you have d of 0. If you plug this in, you have like 0. So in this sense, there is like a still very special point, namely this cusp point where the derivative vanishes. So this will be quite important. And actually, we don't want to look at curves that have properties like this, which are like going down and then have like these cusp points. We just don't want to look at them because like you can't do differential calculus with them. They are like very hard to control. It's like very hard to say, if you think about it already, like what is the curvature of the curve at that point? Like that question geometrically doesn't make much sense, right? Like if you have like things like going in and outwards, it makes sense to say like this curve is like bent slightly in this direction here, right? Like you just like from the picture. But what would be the bending of that curve at the point where it's like going like this? So we want to rule points out where we have the derivative vanishing because they are not nice. And so we would like to look at certain subclass of curves, and these are called regular curves. We have a curve, it's called regular, if C of t is never 0 for all points where it's defined. So geometrically, this corresponds to no cusps or corners. So that's like the general definition essentially of the curves that we will look at. It's like these parameterized curves, and then we require that like the derivative, important, that the derivative is never vanishing. Okay, and now we would like to talk about the length of a curve. And for that I want to recall two notions. First of all, we need to measure the length of a vector in order to make sense of what the length of a curve is. And the first thing is like that we have a scalar product on ein, which is defined by my notation is like with these angled brackets. Just take like the product of all the entries of the vectors and then sum them up. So that's just like the normal scalar product that you should know. And the norm, or the length of the vector, which is my notation for this one, is two double brackets, where you just take the inner product of the vector with itself and then take the square root. And the formula that we all know is that we get a formula for this. So that's essentially the length of a vector. And now how can we use the length of a vector to define the length of the curve? So the idea is we want to define like how long a curve is. And what we do is for this is we choose certain points and then we just measure, as an approximation, we measure the length from this one to this point by just like taking like the straight path and then from this part to this and so on. So that's like just like the straight lines. And we take the length of this and then we make like these points that we choose finer and finer. So in the limit, we get something that is like really approximating really well the length of the curve. So let's say that this one is C of t of 1 and this one is C of t2 and so on. Then approximated by what you have is like you take the difference between C of t1 minus C of t1 and then you add up like so on for the whole approximation. And the point here is that if you make like T1 or like T2, you approach like very closely T1, is that like this vector, which is like the difference between these two, is very much like approximated by the derivative, which is going in this direction. So if you move C of T2 very close, you make like T2 very close to T1, and this difference here becomes very close to the derivative. So this one is very well approximated by the derivative of the curve at T1. And similarly, if you make this one, then this one gets approximated by the derivative at that point T2. So if you move this one here. So what that means, like if you add more and more breakpoints where you measure the length, that means that you get essentially the derivative. And what happens then if you sum up all of these different parts and like the time interval gets closer and closer to each other, then of course the sum turns to an integral. So what we have derived here is that the length of a curve should be an integral over the first derivative. notice is like a capital L of the curve. And what we have is that the interval is from A to B. Then this one is the integral over all of A to B. And then we have to take the norm of the tangent derivative, and we integrate over T. So that's the formula for the length that we are concluded by this kind of like approximation procedure. Just to give you an example, let's look at the circle again, which is already erased. But if you we calculated what the first derivative looked like, and it was cosine and sine, so it was 2 pi, and then the square root of cosine of t squared plus minus sine of t squared dt. This one is just 1. Sine plus cosine squared is 1. So the integral is just 1. So we get just that it's 2 pi, the length. So that's a very nice derivation of how you can calculate like the length of the curve or like of the circle. So question for you, does it depend on the parameterization? So if I have two objects that have like the same curve, but like have two different parameterization of that, do we get like the same length of it or two different kind of lengths? I think that's a good question to go in a break. So I think we continue in 10 minutes. So that's 15, let's say. And yeah, then we talk more about like the lengths and the different parameterizations. Yes.
Look at this curve. Does it consider a smooth curve if we write in this way?
Yes. So in this way, it's really like a smooth curve because, if you take the derivative of this one, it's like this, and if you take another derivative, it also, and it's always nice and like a nice curve, well defined everywhere. So it's really just like if you have like the square root, which makes it non-smooth. So this one is like a perfectly.
But the image looks.
Yeah, so that's like really the point here. Is like the parameterization can be smooth, but the image is not looking smooth. So it's really like important that the parameterization is smooth, and the image can be have like a cusp. So that's like the point.
I've heard if the derivative both element is 0, there will be a bad point.
Yes. Yes. So that's like happens here as well, right? Like if you have like both of them are 0, then this curve is like like at that point like the velocity is 0. So that's why we define these regular curves as like where the points like the curve always has like non-vanishing derivative.
Thank you.
Welcome. So this one should work hopefully. Okay, let's continue. Okay, let's continue. So what we've seen so far is like that we define the curve really of a parameterized curve. So it would be now interesting to see if it really depends on the parameterization order of the image. And one easy way to reparameterize a curve is like to choose a different kind of parameterization is by using what is called a diffeomorphism. So we have like a map that say is phi. It's defined say from, just check the order. It's defined between two intervals where of R. So these are two intervals, and the map of that form is called a diffeomorphism. If it has two properties, if the first property is that phi is bijective, projective, or a different word for this is it's one-to-one. So that means like each point in one interval has exactly one other point where they belong to. So if it's bijective, then there exists an inverse. That says like where a point in I1 in the first interval corresponds to the second one. So that's one. It's a map that goes in the other direction. Exists. And the second requirement that we can talk about a diffeomorphism is that this inverse is also smooth. So we have a map that maps like one point in the interval smoothly to another point in a different interval. So we have like interval here and some interval here. And this map phi maps like this point there to this different point. And then the inverse maps this point here back to this original point. And we want that in such a way that both of these maps are nice, like they have like all of them have like continuous derivatives. So that's when we call them a diffeomorphism. And if you combine one curve with such a diffeomorphism, you get what is called a reparameterization. So if phi is a map from diffeomorphism, and we have one curve which we say like is defined on the first interval. Then also so if you have already a diffeomorphism and one other curve, then you can compose the times and you can change like the way you navigate like through time to get a different curve. So in a bit more abstract picture that looks like this, we have our curve C1, which is defined on some interval I1, and then gives you some points in I. And what we also have is this different kind of map phi, which is defined on some different interval. And then you map first into this interval, and then you get like with the curve, and this map that we get like by composition is then the second curve, C2. So that's a map that is defined on I2 and then maps to IN. So like geometrically or like physically what happens is that you can imagine C1 as a certain parameterization, like say I move now in the straight line and I do that like relatively slowly. So that's like a parameterization of the straight line. But I could also like go very fast. So I change like the way that I go in a straight line, but I do it like on the same path. So that's like this changing of like the speed that I measure my time is given by this map. So of course I can like physically I can't change what time is, but I can change the measurement of time, so to speak. So that's like related to how you measure time or what is your concept of a time. That is kind of like encoded in the reparameterization. So this second curve C2 is then called reparameterization of the first curve. So you have two curves which are like the images are still the same, but like they have different parameterization. That's why we say like it's a reparameterization of the curve C1. And of course, like the velocity changes, right? Like in this example, I was way quicker at some points than on other ones. But like the interesting part is that the length of the curve does not change. And that's like kind of like a small result. So let's calculate this. So let's try to relate the length of C2 to the length of C1. And for this, we need to take the derivative. So we have, just recall that C2 was defined as C1 phi of t. And now we take the derivative. So we take the derivative with respect of t of C2. I think every one of you knows like the chain rule. So we first take the derivative of phi. So it's phi of t composed then with the derivative at the point phi of t of C1 of S. So let's say C1 was like the parameter was called S, and the parameter of the curve 2 is like T. So that's like the chain rule, where you take like the inner product first, and then you multiply this one. So now we know the derivative, or like the velocity of the second curve in terms of the velocity of the first curve. So we can calculate the length of the second curve. The length of the second curve is like the integral over a second interval, say like it's from A2 to B2, and then we take the norm of the first derivative. So that's just the definition of what it means to take to calculate the length of the curve. We just take the derivative of the curve, the velocity, take its norm, and then integrate. So now we already calculated what this one is. So we just plug this in, and then we see that this one is a smooth, like a factor. It's just a number. So we can plug this out of the norm and get like the absolute value of it. So by using this formula, what we get is that it's the absolute value of phi of t times the norm, and now the norm of the second one. now we would like to relate that integral to the length of the curve C1. And what we need to do for that is we need an integral over the parameter S. So we need to change the parameterization. But if you remember how you changed like reparameterizations, it's exactly that you change the integration in there from S being phi of t. So if you change this the integration to S, then what you get is exactly A1 here, because it's you have to plug in the boundaries. And then what you get is that you get the integral here, and then this one gives you exactly d of t comes out. So what you get actually is so that's the reparameterization of the integral by just using this as the representation. And that one is just by definition the length of the curve C1. And that's the statement that we wanted, is that the length of the curve C2 is the same thing as the length of the C1. So phrased in a different way is that like the length of a curve is like not depending on the parameterization that we use. So maybe like the length is like an invariant under parameterizations. So that's maybe already like a first like example of like where you see, for example, the velocity at some point depends on the parameterization, but certain other elements like geometric things that we can define, like the length of a curve, does not depend on the parameterization. And that will be something that we also see later in the surfaces where everything gets more complicated, that there are certain way of like describing a surface and certain elements are nicely defined like independently of the way that we parameterize points, but other elements, which like for example the velocity, really depends on the way we parameterize them. So that's like something that you should like always keep like in the back of your mind as like a small table in some sense of like saying like, okay, velocity is somehow like a little bit bad because it depends on the parameterization. Length is really nice because it's like independent of the parameterization. So it's always nice to have like a mental catalog of like two boxes where something is like depends on parameterization, gets in one box, and the other one's like independent of the parameterization gets in another box. That's sometimes nice to have like as a mental image. And one advantage of like of this concept of reparameterization is that you can ask yourself, okay, if I have one curve, can I reparameterize it, or can I find like a parameterization so that certain elements are really nice, or that I can like study that in a certain nice way? And one of the simplest curves are things where they have unit speed. Like you see, like in the integral of the length, like the easiest integral that we can calculate are the ones where this length here is already 1, because then it's just like the integral over 1 is just the difference between the integrals. So so that will be a certain class of curves which are really nice, for which we can calculate the length really easily. These are like the unit speed curves. curve that has like a special property that the length of the velocity vector is always 1. It's called a unit speed. Speed curve. Or alternatively, like curves with this property that like the velocity is always 1 are ever called a unit speed curve, or some books also call them, say that like the curve is parametrized according to arc length. So what is arc length? The idea behind that is that you have this one is a big curve, and you have a certain point here, say C of A, and some other point here, which is C of B. Then this part between these 2 points, this one here, the red part, is called an arc. So it's like just like part of the curve is sometimes called an arc. And then if you calculate the length of this arc, if it's like a unit speed curve, then this one is just the integral from A to B over 1 dt. So this is just B minus A for unit speed curves. So if you have a unit speed curve, then the length of each arc is just like given by knowing the endpoints. And that's why these called parametrized according to arc length, because essentially time gives you how long the arc is between these 2 points. It's like given exactly by the difference between these points in your parameterization. It's like really giving you information about the length of that particular arc. So that's why they are also sometimes called parametrized according to arc length. But usually I stick to unit speed because it's shorter. But some books like call them differently. And maybe like for today the most important result is the following. That tells you that you always can reparameterize a curve in a certain nice way under very general conditions. And that's every regular is important, curve C so that means you can reparameterize. So that the curve was defined in some interval. such that the curve which is given by so we define a second curve. So yeah, maybe call it like this, of a phi. So we have a different reparameterization of the first curve, and this different curve has like a unit speed curve. So we need to find such a diffeomorphism or construct that diffeomorphism. So we need to construct such a diffeomorphism. So let's go to the proof. So the idea is that we choose some time instance, t0. So we fix one instance in the time and define a map. Which is psi of t, which is the integral from t0 to t over the velocity. So that gives you, in some way, like geometrically, if you have the curve here, then you fix t0, which gives you c of t0, and then this map here tells you the length of that arc. So you get an arc here, and this one has length given by psi of t. So the psi of t measuring like the length of this particular arc. Let's calculate the derivative of this map. Then what we do is take the derivative with respect of t, psi of t. I think every one of you should know that. Like if you take the derivative of an integral with respect to its upper limit, you just get like the integrand back. So this is just like we get our norm back. And what we know is that this one is always zero, not zero, because that's by assumption. By assumption, our curve was regular. So that's like where we use the regularity, is that like velocity is never zero. And then I'm not sure if you had that. Like the people that had like mathematics definitely know the theorem, but some people of you might have not heard it. Is that if you have a map which is well defined and which is has not vanishing derivative, then you can always find an inverse of that map. So that's the standard theorem of calculus. Psi of t, the inverse, which we call phi. So we can actually invert that. And moreover, we can actually also calculate its derivative, which is so that's like an abstract version of like the implicit function theorem, is that you say like the derivative of that inverse is given by 1 over the derivative of the function. And now we know this one already. We calculated it just, right? Like it's like the derivative of this one is 1 over the length of the curve, which is 1. So we have a feeling of the derivative of that phi, which is awesome because we would like to define our curve as the composition of the map C with phi. And if you want to then calculate the derivative of like the velocity of that curve, you need the derivative of phi, which we got by this kind of calculation. So we can put everything together. So the curve C tilde, which was defined over there, has speed, which we calculate again. We just use the chain rule for that. So that's d of dt, phi of s, times the derivative of s, of phi. And now we can plug in everything together. So this one we just don't know because it's, but it's like the first derivative. So that's this. See, don't know much about this one, but we just calculate that this one, the derivative of phi with respect to s, was given by 1 over. And so you see here, like quite a bit by construction,